I guess the goal for today is to have a webinar on the basics of acoustics and noise in the context of noise regulations and, for industrial and commercial type sites. And just so we can have a common language and terms about how it all fits together and a basic understanding of noise. And we'll go from there. So what we're going to cover today, we've got about 5 or 6 topics. What is sound? And we all know what sound is, but I'm talking from a physical and scientific perspective. What creates it and how does it behave? We're going to talk about sound pressure level and decibels, which are terms you've probably heard. That's how we quantify sound, important to talk about before we talk about impact and regulations and so forth. Acoustic frequency, and some terms you may have heard of, dBA, dBc, and dBz, what they mean and how we use them. Sound versus noise versus vibration, and noise criteria or noise limits. A little bit about low frequency sound, and time permitting, we'll talk about noise control strategies as well. It's a lot to cover. I hope we can do it all within an hour and still have some time for questions. So a couple of house cleaning things. I'll try to leave 10 or 15 minutes at the top of the hour for questions. I think some of the material is somewhat optional, although it'd be great if we could cover it all because I think it's all relevant to your current context. But please interrupt me as we go if there's something that's unclear, because we've sort of set this up so that successive slides depend a little bit on what we talked about in the earlier slides. So if something's confusing and I haven't explained it clearly, please stop me and ask, and I will try to clarify. And then questions of a more general nature we can handle at the end. So just at the outset, who HGC is, we're an acoustical consulting engineering firm. We're one of North America's largest, and we were founded in '94 and headquartered in Toronto, Canada. And that's worth mentioning because it is one of the most highly regulated jurisdictions in North America with regard to noise. And we've had very long-standing and fairly restrictive noise limits. So that's not always a great thing for us, but it does mean that as acoustical consultants, we've been dealing for a lot of years with some of the things that some jurisdictions are still just getting up to speed on. And we have branch offices in Charlotte, North Carolina, Dallas, Texas, and Calgary. And I actually think 2 of my colleagues are on the line with me today. Nick McCabe, who heads up our office in Charlotte, is on with me as well. My name is Rob. I've been with HGC almost since its very beginning, 36 years ago. Well, it was about 32 years ago. I've been doing noise consulting for about 36. And work with all sorts of facilities, primarily working in environmental industrial. As a firm, we do all kinds of things. We do building noise, infrastructure, architectural acoustics, all that good stuff. The group I work with here, we do environmental, we call it industrial or industrial commercial type noise. So that's power generation, oil and gas facilities, mining, all kinds of things. And increasingly, as you might imagine, over the last few years, data centers as well. So what is sound? Well, in a scientific sense, sound is air pressure fluctuations. So now I'm going to ask if somebody can speak up. Can you see this little picture animating so that you kind of see waves going from left to right?
Yes.
Okay, good. Wasn't sure if that would come through on video or not. But sound is really air pressure oscillations. And so we say scientifically compressions and rarefactions. So the air molecules get more dense and less dense, and they vibrate or they pulsate in that fashion. So something creates a sound, and we get a wave like this traveling through the air. The interesting thing to note here, if you look at the little orange dots, if you can see them, and the orange arrow, the molecules themselves aren't traveling per se when sound is moving through the air. They just wiggle back and forth. But these zones of compressed or bunched up air molecules and spaced out or rarefied air molecules, in a theoretical sense, those zones do move. And so you can see, if you look at both of the black dots and the orange ones, or the black arrow and the orange ones, you can see that those zones move through the air, even though the molecules are just wiggling back and forth. And so a wave does travel. And if I create a very short instantaneous sound, a clap or an impulse, we'd really just have one of those little darkened zones, the compression zones, moving away from the source. What we're seeing here is a continuous source. And the little wave we're looking at underneath, that's a sine wave, like a pure tone, somebody whistling or playing a note on a piccolo. And so we've got these multiple wave fronts because the sound is persisting for a period of time, and we've got a traveling wave going through the air. And more specifically, though, sound, by sound, we mean audible air pressure oscillations. So, in other words, we hear those pressure oscillations with our ears if the oscillations happen at a rate of 20 per second up to about 20,000 per second. And for oscillations in the air that are slower or faster than that, we don't hear them. And in this picture, that fast wiggling waveform going up and down. So this is what you'd see if we took a microphone and we stuck it at a point where there's sound waves passing by and we graphed it. And so we're graphing sound pressure versus time, sound pressure on the vertical axis and time on the horizontal axis. Excuse me. And so those fast wiggles, those are the wavefronts moving by. And the straight line through the middle about which everything vibrates, that's actually atmospheric pressure. So we're getting little ripples on top of the steady, unchanging atmospheric pressure, or very, very slowly changing atmospheric pressure. And so when the peaks wiggle up here, those are compression or pressure zones. And then down at the bottom where they go, where it falls below atmospheric pressure, those are the rarefactions, right? And they're happening quite rapidly in the range of 20 to 20,000 oscillations per second. And then this bigger variation you see here, that is the outline or the envelope of the wave, that's telling us that this isn't exactly a steady sound. I mean, it's persisting in time, but it's bigger or louder here, and then it kind of goes quiet, and then goes a little bit louder again, and then it goes quiet, and then it goes louder again. So, maybe that's somebody saying sounds are waves. So we kind of had three distinct sounds there, and it got quiet in between. So that's the kind of thing you'd see if you hooked a microphone into your computer and just graphed it versus time. Simplified. Now, when we talk about sound pressure level, like you'd measure with a sound level meter, or loudness of sounds, we're really talking about the envelope of that wave. And I've drawn that in here as kind of a purple line. So we're not hearing individual wiggles. To us, that's just a tone or a sound. But as the height of those wiggles, the magnitude of those gets larger and smaller, the sound gets louder and quieter. So what we've graphed up here in kind of stylized or simplified form is not a steady sound. This is a time varying sound. And we're going to show variations on this graph throughout the presentation. And we're going to draw some interesting information from them. So that's kind of what sound is and how it moves as a wave. Let's talk about sound pressure level and the units of measuring sound pressure levels, which are decibels. And I'm sure you've heard that term before. But let's talk a little bit about what that really is. So the audible range of loudness from the quietest to the loudest things we can hear is enormous. It's more than a factor of a million. We can hear from 20 micropascals, which is a very small pressure ripple fluctuation, all the way up to 20 million micropascals. And that's almost a staggering range. And those numbers are so small and so large, they don't make a lot of intuitive sense. So we don't, for the purposes of talking about loudness, we don't talk about sounds in their primary units of pressure, pascals or atmospheres or PSI, depending on the units you want to use. Instead, we do a little mathematical transformation and we deal in decibels by taking the logarithm of the pressure value and dividing by reference. So we're not getting today into what the math is behind decibels, but what it does is it condenses the range from this scale of 1,000,000 down to about a scale of 100, or at most maybe 200. And that ends up being much more intuitive, and it makes a easier set of numbers to work with. Another thing that's a little esoteric, I won't get into too much explaining, but it also makes it reflect more the way that we hear it in terms of loudness, because we hear in a logarithmic way, both in magnitude and acoustic frequency. So what that means is for every equal factor or multiplication, every time we go up an order of magnitude, that sounds roughly like an equal increment to us in terms of loudness. So the decibel is handy in two ways. It makes the numbers more intuitive, and it also then corresponds more to changes in sound level in the way we hear. And so here's a little scale showing common sounds and the pressure that we talked about in pascals, and the factors and what those different things are. And it's so small on my screen, you can barely see them. But we normally say that the threshold of hearing, 0 dB, is about like the tick of a watch at 10 paces in a quiet room. And so that's about 20 micropascals. And we just arbitrarily, well, not arbitrarily, but because that corresponds roughly to threshold of hearing, we set that as 0. And then we go up from there. So you can see that as we get up, we get into some very loud sounds when we get into the 80s, 90s, 100s, and then we get into the painful or damaging levels much beyond that. Even short-term exposure at much over 130 or 140 can cause permanent hearing damage. And it's not really shown here, but we can actually have negative decibels. And that doesn't mean that sound is getting sucked out of the environment. That just means that there are sounds that are quieter than 0 dB that are generally not perceivable by humans, but you might be able to measure them. So we can actually measure sounds that are minus 10 dB, very, very quiet. Even in an anechoic chamber, a very quiet room, we can still measure a little bit of sound that you might not hear. And if we look at that same bar graph again, it's just interesting to note that you get into the pain threshold at about 120 dB, something like that. The risk factor for hearing loss or risk of hearing damage due to long-term exposure happens between the 80 and 90, around about 85. And so that's why a lot of workplace noise limits are set at 85, because if the levels aren't greater than that, then the risk of hearing loss with age, just due to aging alone over a career, normal working career of 30 or so, 30, 40 years, is about the same whether you were exposed to that sound or not. And if you get above that, there's a measurable increase in risk of hearing loss. So that's the way they came up with that regulatory limit. And then much lower than that, though, are the typical limits for environmental sound to avoid disturbance to neighboring communities. That's in and around the 40 to 50 range when the background sound is quiet, when you're in a quiet environment. If you're in another environment where there's a lot of background sound already, then you can go a little higher because maybe you won't notice the industrial sound over the natural sounds or road traffic or that sort of thing. So, you rarely see sound levels lower than, I'd say 10 or 20, and rarely do you see them over 100 or 110. You're getting up into really loud above that and really, really quiet below that. So that's the decibel range. There's some really interesting rules of thumb, useful rules of thumb that we can keep in our back pocket using decibels. One is that a change of less than about 3 decibels is generally imperceptible to most people, other things being equal. So if you just had a stereo and a loudspeaker and a volume knob and you turned it up and down by 3 dB, virtually no one would be able to hear the difference in that. Conversely, a change of plus or minus 10 dB equates to about a doubling or a halving of perceived loudness. And by extension, we can sort of say, if you go up by 10, so say from 30 to 40, 40 is going to sound twice as loud as 30. And then if you go up from 40 to 50, that's twice as loud again. So that's 50 is going to be 4 times as loud as 30. And if you go up to 60 dB, that's going to be 8 times as loud as 30, and so on. It's also, I'm not going to get into this. The math is a little squirrely, but decibel addition, we have to remember, is different from arithmetic addition and subtraction. And the joke is, if you have 2 dB and 2 dB, the answer is actually 5, not 4. And here's why. I'm not going to get into the equations, but if you have two sounds, each of x dB, arriving at the same point, they don't sum to 2x, but they sum to x plus 3. So if we have 50 and 50 arriving at a point, it's going to be 53. If we've got 40 and 40 arriving at a point from two different sources, they're going to add to 43. If we've got background sound of just birds and breeze in the trees and crickets of 50, and we have a power plant making 50, those two will add up to be 53. And the interesting thing to note about that is 3 dB is also about the threshold of perceptibility. So, generally those two things make more or less you add the two, it's imperceptibly louder than the one alone. We have to use the logarithmic addition, not arithmetic addition, when we're dealing with decibels. We don't have to get into that today, so that's fine. But one notation we'll see is just to keep track of how we're adding, we often use a double plus, just to sort of say, oh, we're doing logarithmic or decibel addition here. So 50 dB plus 50 dB is 53 dB. So in general, anytime you have two sound levels, you add them together, they're equal, they're going to be 3 dB louder. Here's another, oops, I jumped all the way to the end. That was bad. We'll get back to where we were. Sorry about that. Hit the wrong button. Bear with me one sec. Here we go. Okay, some other cool stuff, important stuff to know about decibel addition is that if you have two sounds that are 10 dB apart, the quieter one doesn't even add into the louder one. So if you add 50 and 40, you just get 50. Now, actually, we get 50.4, but we round it to 50. And for all intents and purposes, once you have two sound levels more than 10 dB apart, they don't really, the lower one doesn't really add in. Because in this case, 50 contains 10 times the acoustic energy as 40. So once we do that logarithmic addition, the smaller one is so small, it really only tips it over by less than a full decibel. So we generally say when two sounds are 10 dB more apart, quieter one effectively doesn't even contribute. And that's why it's one of the reasons that one louder sound can utterly mask the quieter sound. If it's 10 dB louder, it has just an overwhelming more amount of acoustic energy in it. Makes the smaller one almost irrelevant. Now, we're going to get into acoustic frequency. Before I do that, are we all good? Does that all make sense? Anything unclear so far? Okay, I always take silence as a resounding yes or vote of support. So we're going to forge forward. So everything we've talked about so far really has been to do with the magnitude or the loudness of the sound. Frequency is a different parameter. It's the other important parameter or dimension that we need to talk about when we're dealing with noise. So in addition to level or loudness, we can also detect differences in frequency, which is tone or pitch, like what musical note does it make, if it does. Acoustic frequency is the rate of pressure oscillations, how quickly they occur. And we alluded to that saying that below 20 and above 20,000 oscillations per second, we don't hear it. But there's more important going on than just that. The unit of measurement is hertz, named after a famous physicist. But really, hertz just means cycles per second, or oscillations per second, or vibrations per second. So 20 hertz is 20 vibrations per second. So we have low frequencies, and in this pictograph, I'm showing a tuba and a sound wave. And again, we're looking at sound pressure on the left-hand side and time on the x-axis. So that's the way the sound pressure varies over time coming out of a tuba compared to a piccolo, which has a lot more vibrations or oscillations per second. And I mentioned time across the bottom and pressure because we're going to get into some graphs eventually where we're looking at acoustic frequency across the bottom, and that's a bit of a different scenario and concept. So I'll let you know when we get there. When we talk about frequency ranges, this is actually kind of a hybrid graph because I have graphed it as if it's a wave in time, but I put some frequency markers at the bottom to kind of show you roughly how these wiggles would correspond to the different frequencies and what the frequency ranges are. So if we've got this wave, and you can think of this as if I was sweeping a tone, like playing on a slide whistle and starting at a really low note and then getting up to a very, very high note over here. This would be the audible range here, going from 20 hertz to 20 kilohertz or 20,000 hertz, right? And within that, we talk about low frequencies, usually about 100 hertz and lower is kind of what we refer to, maybe 200, something in that range. So 20 to 100 or 20 to 200, that kind of range, that's low frequency. Mid frequencies are from that point up to about a kilohertz. These are not hard, rigidly defined terms, but that's kind of the ranges that we use in normal acoustic conversation. Up above a kilohertz, all the way up to 20 kilohertz, those are high frequencies. Why is that important? Well, for a couple of reasons. One is that, as we're going to see, we don't hear all those frequencies equally well. And also, all of those frequencies, anytime sound travels from point A to point B, almost all the mechanisms that influence how much sound gets from point A to point B, they affect the different frequencies differently. And there's physical reasons for that. It has to do with wavelength. So the lower the frequency, the longer the wavelength is in physical space. And so that changes all kinds of things, like how well obstructions will shield the sound and how much gets soaked up in the atmosphere, how much does wind affect it, all those things affect the different frequencies differently. And then the other important thing to put on here are those little ranges above and below 20 hertz up to 20 kilohertz, where we can't hear it. Doesn't matter how loud it is, our ears are not built to detect oscillations in that range. Sometimes when it's low frequencies and very high intensity, you can feel it palpably, perceptually, but you don't hear it as a sound or a tone. Now, most sounds don't contain just one frequency. They contain lots of frequencies. They contain a mixture. So, for instance, here we have a multi-frequency sound created by a little ensemble of musical instruments. And so there's going to be some high frequencies and some low frequencies and some mid frequencies in there, all adding up. And this is the kind of complex wave you might get. Now, it's complex, but it's still quite regular and well-behaved and smooth. And that's because when we're dealing with music, the frequencies are usually integer multiples of one another. And so they add up in a way that creates a fairly well-behaved waveform, and we find it to be harmonious. And the word harmonious derives from the word harmonic, which actually has to do with being an integer multiple of one another. Conversely, a lot of unintentional sounds or sounds that are less designed have non-integer multiples between the various frequencies composing them, and they wind up with a much more random and harsh-looking waveform, and that's a dissonant combination of the different frequencies. So it's worthwhile kind of pausing at this point to say, a common definition of noise, maybe the most common, is that noise is just unwanted sound. So sound is pretty physical. We can know with pretty clear certainty, regardless of the listener, what sounds are going to be perceivable or not, but whether the person thinks it's noise or sound is somewhat personal, depending on a whole number of factors. I'll bring that again. We do have sounds that generally have more pleasant character because they've got a simpler, more harmonious or harmonic combination of different frequencies. And we've got harsher sounds that are a more random combination of frequencies. But that alone doesn't determine whether it's sound or noise. Because, even pleasant music, if you're trying to read a book or concentrate or have a conversation, might be unwanted. It might be noise in that context at that moment. So the definition we stick with most frequently in the field is that noise is unwanted sound. Now, I mentioned that the human hearing system, ear and neurological system, is not equally sensitive to all frequencies. And so if we play different frequencies in turn and measure them with a sound level meter and they are all equal, let's say they were all 50 dB, they're not going to sound equally loud, even though they have the same magnitude if we were to graph it, the same degree of pressure fluctuations. Because the ear has a frequency response and it's not flat. It's kind of frown shaped. We'll look at it in a sec. And it's referred to as the A curve. And we apply the A curve to if a sound has multiple frequencies in it, we apply that A weighting curve to all the different frequencies, and then we add all that energy up into a single number. And that's one way of taking all those different frequency components that each have their own loudness contributing to the overall sound and weight them in a way, and we add them up, it corresponds to how loud it is. Here's a graph of what the A weighting curve looks like. And now, instead of time, we're looking at frequency across the bottom, down from about as low as we can hear up to about as high. And you can see this is how it's weighted. It's arbitrarily set to be 0 at a kilohertz. So relative to the sounds that we hear at 1,000 hertz, we hear with much less acuity at the lower frequencies. You see it rolls off. And at 31 hertz, getting down close to the lower frequency that we can hear at all, it sounds about 40 dB quieter than the same magnitude of sound at a kilohertz. And if remembering our rule, if we go down by 10, that's a halving. Down by 10, that's a quarter as loud. Another 10, an eighth as loud. Another 10, it's 16th as loud. So with the same unweighted dB sound level, 31 hertz is going to sound 1/16th as loud as a kilohertz. Then it's pretty flat for a while, and it rolls off a little again at the high frequencies. Now, why is that? Well, I think we've evolved that way. Our ears and hearing system evolved that way for a couple of reasons. One is, if we're being tracked by a predator millions of years ago or thousands of years ago, and a twig breaks as the lion is coming upon us, that happens in and around the kilohertz range. So that's where our acuity is greatest. We've evolved to be able to hear things in the wild that have to do with being tracked or catching prey or finding a mate. And so we've evolved both hearing and vocal systems that are kind of centered in this range. Why does it roll off at low frequencies? Well, because there's a lot of high-level, low-frequency sound present in the environment. In fact, if we could hear all the way down to 0 hertz, fluctuations in barometric pressure with weather would be deafening, or shifting of the tectonic plates. So our ear rolls off so that doesn't obscure our ability to hear in the range where we vocalize, where we hear bird song or animal sounds or natural sounds in the environment that are important to survival. But why do we sum them? Why is it that we weight these sounds and components and all the different frequencies and add them into a single number by energy summation? Well, we do that because, as it turns out, when we take an A-weighted sum, in other words, all those different frequencies, we weight them and add them together and call it a dBA, single number measurement, that's a very good descriptor of the loudness of a sound that contains multiple frequencies, or of two different sounds that have different frequencies. And it correlates well with the potential of a sound to be disturbing in an environmental impact scenario or to cause risk of hearing damage or workplace safety. So it's a really useful way of taking a wealth of information about the sound at all the different frequencies and boiling it down to a single number that's really relevant. Now, there are other weightings you may have heard of. Here we're showing A, B, C, and Z. Now, there are some others. There's D and there's G. B is, I've never seen it used. It's some archaic thing. It's not used for anything. C is still hanging around a little bit. And Z really just means unweighted. So we've drawn it here as a green line. So dBz weighting means we've just taken all the different frequencies of sound, we've added them up, irrespective of how they impact the human ear. That's the total amount of sound energy. It's useful for some things when we're summing, but not all that useful. C is kind of it's also a little bit archaic. It's almost flat. If you look at C and Z, they're almost the same. B and C roll off a tiny little bit at high frequencies, but so C is almost flat. It rolls off a tiny bit at the low and a tiny bit at the high. Why is it doing that? Well, C weighting and A weighting, they really came from the days when we had analog sound level meters before digital era. So, if you wanted to, with a sound level meter like that, if you wanted to know the sound at different frequencies, you would have to have a knob on the front with a cumbersome set of electronic acoustic filters that you would click through. You could click from A to C, or you could even click through individual frequencies, but it was very cumbersome. And if you wanted to store the number, you'd have to write down a whole different set of numbers at each different frequency. So they came up with these weightings, and C was very close to an unweighted sum, but it rolled off a little bit at the low end so that wind and really low frequency noises didn't obscure the measurement, and the really high frequency noises. But so we'll talk a little bit about C later, but it's really kind of archaic and not all that informative. A is still useful to today because if we take all those frequencies and add them up, it gives a really good indication of how loud it is. So in the past, back when we had analog sound level meters, before we had digital ones with convenient, fast digital filters and the ability to store the data internally on a sound level meter, we sometimes use dBc or the difference between dBc and dBA to get an idea of how much low frequency content there was in a sound. And so still in some places you see noise ordinances and regulations with a dBc limit, but it's kind of archaic and not all that useful in my opinion. And that's partly because there is no clear noise response or dose response relationship for the B and the C and the Z weighting. They're useful for special little things, but unlike dBA, which was derived from the human response to noise and the frequency weighting of our ear, those other weightings don't have that same benefit, and there's no real correlation between them and the ability and the potential for a sound to be problematic in one way or another. Now, before we leave our discussion of frequency, we will talk about situations where we do want to look at frequencies individually. And the most common is, rather than weighting and summing up all the different acoustic frequencies, we kind of measure them all separately. And here's the most common way to do it. This is called octave bands. You might have heard of that as well. And so again, we've got frequency across the bottom. And what we can do is cut up the audible spectrum into bands or strips and measure the amount of sound and just sum the energy in each of those bands. And these bands aren't equal width in hertz, but they're equal percentage width in hertz, because again, that's the way we hear acoustically. And they're called octave bands because each one goes up by a doubling of acoustic frequency, which happens to correspond to 8 musical notes of the Western scale. So, if you started on C, you go up an octave, you'd still be on C, but you'd be an octave up and so on. So they actually get their name from musical theory, but they're frequency bands that cut up the audible spectrum into these bands, and we get a dB number for each of these. In North America, it's customary to show those in unweighted or dBz form, the individual frequencies, and then weight them and sum them into one overall. So these bands, if you weight them with that curve and you decibel add them, they will actually add up to this number here, which is so small on my screen I can't see it, but trust me, it is. So why do we need to measure in separate bands like that? Well, there's a few reasons. One is that although an A-weighted sum is a good single number for assessing the severity of a noise and maybe evaluating whether it's acceptable or is it going to bother somebody or is it risk for hearing loss. For the more detailed purpose of analyzing sound, we need to look at the individual frequencies. As I mentioned before, all of the mechanisms that affect sound propagation from point A to point B affect the different frequencies differently. So when we as acousticians do the analysis, we have to do it in parallel on all 8 or 9 or 10 of those octave bands, or sometimes we even do it in third octave bands for greater granularity. And then once we've figured out how it gets from point A to point B, we then add it up, weight it, add it up and say, okay, how loud is that going to sound to somebody? And similarly, if we're designing noise control, we have to be very aware of that because the different frequencies that are left over by the time it gets to point B, they're telling us which frequencies need to be attenuated, and so we can't. We need to use that information. What frequencies are pushing the dBA over the limit, and then we have to control those frequencies. And finally, the risk of some other interesting things like induced vibration from high intensity, low frequency sound. That's a very frequency specific phenomenon. And using dBA, even using dBc, is really not adequate to identify that risk and to design to avoid it. And then here's just a picture. We don't always work in full octave bands. Sometimes if we're concerned about pure tones and humming, we actually look in finer frequency resolution. Here we're showing 1/3 octave. And then we've also sort of shown dotted lines on here of which triads of third octave bands would add up to give you one full octave band. Okay, and that's the end of our section on frequency. Any questions there? Anything unclear before we go on and use all that information to talk about sound and noise criteria and so forth? Okay, and we'll move along. I think we're doing okay for time. We're about halfway through. So the basis of noise criteria. I think it's very important to say at the outset that when we're talking about regulating noise or figuring out what's a reasonable target for some new man-made noise source, important to keep in mind that inaudibility is not a realistic or a necessary basis generally as a noise limit for technological human society. All human activity, including technological human activity and industrial activity and transportation, produces some amount of noise. And if we say that the limit's got to be inaudibility, you won't be able to operate anything anywhere near any other person. It's just not practical. And thankfully, it's generally not necessary. Our goal here is not to try to create a natural in nature environment for everybody. In fact, nature itself isn't all that quiet either. The goal is to create an acoustic environment that is acceptable and doesn't hinder people's life, enjoyment of their property, and health and safety. So instead, limits are intended to allow a reasonable amount of noise, quiet enough to be unlikely to disturb. If you remember when we had our little noise thermometer, sure, there's noise levels for protecting hearing, in a direct physiological sense, but that's much, much louder than would be acceptable just for an ability to rest, relax, and enjoy one's own property. So environmental sound level limits, whether it's for traffic, air traffic, industry, infrastructure, or for that matter, parades and parties and all those sorts of things, they're set at a level quiet enough to be unlikely to disturb. There is that personal and qualitative. I hesitate to call it subjective because it is predictable, but the personal element that depends on people's acuity and their relationship to the producer of the noise, those will affect what level is likely to be or unlikely to be disturbing. But we can talk about that in a couple of slides. So in that way, when we come to set sound level limits or noise criteria for an industrial infrastructure project, the idea is they need to be able to contribute to the acoustic environment, but not to dominate it. And that's the way that most noise limits are based. And we can do epidemiological studies on dose response relationships to find out what the majority of people find acceptable as a noise level. But before we can do that, we need to talk a little bit about the descriptors and the units of measurement. Because there's many different ways of measuring sound. And a lot of that has to do with the time varying nature of sound. So if we go back to the wave I showed you at the beginning, and we look and we say, okay, remember the fast wiggles are the pressure oscillations themselves, and this slow one that I've marked in purple is the loudness of the sound varying over time. So if I were to ask you, how loud is this sound? Well, there's not an easy answer. It's quite loud, at this early part of the hump here. I don't know if you can see my cursor or not, but I'm pointing to that first bump peak, and then it goes down into the trough and it's quieter, and then it comes up a little bit, and it's a little bit louder, and then it goes quiet again, and then it goes louder, but not as loud as it was. So it's time varying. Bottom line, it's a time varying sound. And when we talk about sound pressure level is an instantaneous quantity. It's changing moment by moment. So how loud is that sound? That's hard to say. It's easy if we have a steady sound. So this is a graph of a steady sound, not time varying. If we draw the line along the envelope, then it's just it's a flat line. That's easy. But a time varying sound isn't so easy. And how do we respond to time varying sounds? Well, it turns out there's a pretty handy measurement descriptor or way of measuring to do that. And it's called the energy equivalent sound exposure level, or LEQ for short. And it is a kind of an average, although it's probably better to call it an exposure level than an average, because it's not an arithmetic average. Again, we're working in decibels, which means that when we take an average, we're doing an energy average. But it is a way of saying what was the sound exposure in a given period of time. So the formal definition of LEQ is it's the hypothetical steady sound level that contains the same amount of acoustic energy in a given period of time as the actual time varying sound level. So these two things, the purple line and the red line, are energy equivalent or exposure equivalent. So that's all fine and well from an energy standpoint, but it turns out that the best correlation that we've found so far for time varying sound to people's response to it is this energy average. So it kind of makes sense. It's how much acoustic energy you're exposed to. Now, we have to be judicious about the time period we pick for it. And spoiler alert, in most jurisdictions, it's either 24 hours or 1 hour, or sometimes the 16-hour daytime and 8-hour nighttime period, or the 15-hour daytime and the 9-hour nighttime period, but reasonably short. And if we take an average of the sound over that time, we can find a correlation then for what level at that averaging period using the LEQ, how will people respond? What will be annoying and what won't be annoying? It turns out, kind of similar to the way dBA works, it's also a good measure of how risky that sound is to long-term exposure. So it turns out that in almost all environmental noise measurements and almost all workplace health and safety noise measurements, they're actually done in some form of an LEQ, an energy average over time. So why do we use LEQ? I guess I kind of spoiler alerted that, but here we go. LEQ correlates well with the potential of a sound to disturb, annoy, or fatigue individuals. So LEQ in units of dBA. So what we're measuring, the quantity that we measure, isn't sound pressure. We measure the energy average, energy equivalent of the sound pressure level in units of dBA. It's the basis of most environmental noise limits, regulations and ordinances, and workplace safety ones as well. Now, for LEQ alone, if we just use an LEQ and we want to come up with an environmental limit to keep all the neighbors happy within earshot of, again, a highway, an airport, a power plant, a data center. If we're just using LEQ, we might need to have separate daytime and nighttime noise limits because there is a greater need and expectation for quiet at night than there is during the day. So many jurisdictions do exactly that. They they say we're going to measure an LEQ, either 1 hour or daytime period, nighttime period, and then we're going to have a dual set of limits, one for day and one for night. That's quite common. Or another approach is to use a kind of a improved or a adjusted LEQ. And that we call the day-night sound level, or the time-weighted day-night sound level, and it's shorted to LDN. It's a kind of LEQ. It's modified to account for the greater need for quiet at night. And the way we do it is we take the level occurring at night, we add 10 dB to that arithmetically. So we just boost it by 10, kind of penalize it if you like. And then we time average it with the daytime LEQ. And so if you had a sound level limit, let's say of 40, continuously all day long, steady, the LDN won't be 40 because we're going to penalize the portion of that happens at night with a penalize by 10 dBA. And so it'll actually add up to about 46, if I've done my math right. So it's a way of using a single number, but making sure that single number takes into account, how loud something needs to be at day and at night. So again, that's one option. Some jurisdictions use LDN. Some use LEQ, but a separate daytime and nighttime. And remember, LDN is a kind of LEQ. It's just got a built-in penalty for the nighttime period. Now, I mentioned LDN in particular because a majority of the work that's been done, sort of the dose-response relationship, and what sound levels are acceptable to most people, has been done using LDN. And here's an example here. So this is kind of this curve has been around since, I believe it was developed in the 70s, originally for traffic sound, but it's been developed greatly since then. There's an actual formula for this curve. It is a fairly characteristic S-shaped dose-response curve for all kinds of stimuli, not just noise. But it can tell you if you've got this kind of an LDN level, here's the percentage of people that are likely to be bothered by or annoyed by that sound. And again, most environmental limits are in and around the 45 to 55 or 40 to 55 range, depending on whether it's day or night or LDN. And very commonly used is 55 LDN. That was actually developed by the EPA in the 70s, and that was sort of recommended as a target for municipal noise ordinances, particularly for, again, industrial or road and traffic type sound. So that really covers the audible, what we think about for the most part, the audible issue with sound and noise, and how loud is too loud, how quiet is quiet enough. There are some other little things that we need to worry about. One of them being vibration and low frequency sound. And I mentioned these two together because they're kind of related. Well, sound and vibration are related, but there's an interesting connection between low frequency sound and vibration. And there's a lot of confusion about what is sound and what's vibration. And when somebody has a concern and makes a complaint, sometimes they might call it sound or vibration, and it might be one or the other. So it's important to sort of clear up the language and the concepts around it and talk about the relationship. So is sound the same as vibration, or is it not the same as vibration? The answer is yes and no in different contexts, but we can make some sense of it. So typically, usually, when we say vibration, we mean oscillatory motion of a solid material. And you perceive vibration by touch, you feel it. And that's a bit different from sound, where you hear it. You can actually pick out a tone, and you might be able to hum along with it. Nevertheless, most sound that we hear, and we could say that sound is vibrating air molecules, but that's not what we usually mean when we say vibration. Usually when we say vibration, we mean something physical and hard solid material that's in oscillatory motion. So sound is sort of oscillatory motion of air. You kind of think of it as vibration, but interestingly, most sound is produced by a vibrating solid object. Because when a solid object vibrates, it pushes the air around it. It sets the air into oscillatory motion, and that causes sound. So there is that relationship. Almost every time you have vibration of a solid object, you're going to have some sound associated with it to varying degrees. Not always the case, vice versa. So sound can be thought of as vibrating air, although sound is primarily heard, which is a distinct, different perceptual mode than feeling it. We can perceive tones with our ears. We can't perceive tones tactilely by feeling the vibration. When environmental vibration is a concern, or when it's perceptible, it's usually transmitted through the ground. You know, when you've got a situation of, oh, it could be a train, it could be a heavy industry. If there's vibration, the only solid way it can get through in a perceptual sense to a point of reception is through the ground, because that's the only solid object or material that's connecting physically the source to the receiver. If it's got to go through the air, it's gonna happen as sound and not vibration per se. And ground-borne vibration is typically only an issue from heavy operations like rail passes, stamping presses, drop forges, or really severe vibratory processes, and usually only within about 100 yards of residences. Now, some severe things like explosions and blasts for mining, they can put vibration to the ground, travels much further. But it's kind of unusual that to have vibration being a nuisance problem at distances greater than that, unless you've got something inordinately, extremely severe. But there is an interplay between sound and vibration. So you may have seen or experienced that very high intensity sound, especially at low frequencies, can induce vibration into solid objects. You may have seen, you know, in high school or public school and science class, where you can strike one tuning fork, and then another one nearby will start to vibrate at the same frequency because of acoustic excitation. So that is possible if you have corresponding resonances. But in reality, in practical terms, it usually has to be a low frequency, because those are the frequencies when you generally get a structural resonance in something like a house. It has to be very high amplitude. And so there are occasional instances where you could have a high amplitude, low frequency sound causing a perceptible vibration problem. And that's really the primary concern with low frequencies, because as we saw in the A weighting curve, our ear weights those frequencies down so much that we don't really tend to hear them. And so they're not as much of a problem for sort of audible disturbance as the mid and high frequencies are. If we go back to looking at that frequency range diagram I had done earlier, I've taken the same range here, but I've highlighted the low frequency range from 20 to maybe 100 hertz, and the infrasound range, where we can't hear sound at all, regardless of how loud it is. Those are the places where if we have very high intensity sound, we want to make sure that it's not going to cause perceptible vibration in somebody's home, which is usually only a concern with weight structures like wood frame single family homes, or now 2 or 3 story with mass timber construction. You could have perceptible vibration. You can also have rattling of lightweight fixtures. So that's the concern about low frequency sound. Not so much that it's going to be heard, but is it going to rattle something, or is it going to cause some perceptible vibration? And so we come back, to these sort of semi-archaic measures that used to be used using DBC or dBA minus DBC to say, do we have a lot of low frequency? Again, the problem there is that because DBC is just mildly weighting and summing together all the frequencies, it doesn't tell you very clearly whether you've got a low frequency problem that's going to cause vibration or rattling in a lightweight home. Even if you have lots of low frequency, or if you've got a big difference between dBA and DBC, it doesn't really tell you much. because it's not frequency specific, and the risk of vibration, perceptible vibration or rattling is very frequency specific. So a much better approach, and the reason that we talked about octave bands, is to look at those low frequencies specifically. And this is a graph of an actual power plant operating in blue versus the background sound in orange, and with the power plant turned on and off. And we've got on here two risk limits for the possibility. It's not a causal thing, it's just a possibility. If we've got a matching of resonances in a wood frame home, we could get vibration. So the interesting thing here is the A-weighted sound level of the facility was quite quiet, in around the 44 dB range, with and without the power plant operating. So it didn't really make a big audible difference to the sound level at all. But when the power plant comes on, we've got some very high intensity, low frequency sound here, creating into the 70s and 80s unweighted dBA at the low frequencies. 16 is actually an infrasonic frequency, right? We can't hear that no matter how loud it is, but it's loud enough, and at 31, where we could still hear it a little bit maybe, that it was not only past the onset of risk for perceptible vibration rattling, it was actually up into the high risk range. So this is an example of a more robust set of criteria. It's a handful of numbers. There's separate criteria at 16, 31, and 63 hertz ranges, and then two levels, risk levels. So that's something that's a lot more, I guess, gaining use, and I think more robust than trying to do a dBA or DVC limit for low frequencies. Now, I am mindful that we're at the top of the hour. We have covered most of the material. We're going into the final section. I've just got a few sort of, I guess, explanatory notes on noise control strategies and type of noise control measures, how they work and when they don't work, and so on. Maybe for anybody has to leave right away, are there any questions we want to squeak in now and take a brief pause between this and the final section, or would you like to just continue on through to talk about noise control strategies? Probably about 5 minutes of material left.
Go ahead and keep going, Rob. I think
Keep
if people
going.
jump off, they can jump off. We're recording it so we can post it later.
Okay, and we can always gather questions by email and
Yep,
send out answers afterwards and so on as well.
perfect.
Okay. Okay, so we've talked about noise, how we measure it, how we evaluate it, how limits are derived and so forth. How about strategies for controlling sound? So broadly speaking, there are four factors that affect the loudness of a sound arriving at a point. I'm keeping it broad here, not necessarily sort of outdoors in the environment, could be indoors as well. But obviously, how loud are the sources we're talking about? Are they quiet? Do they emit a little bit of sound or a lot of sound? That's kind of a primary factor. Second is, what's the distance between where the sound is generated and where it's received? We're going to see, but sound spreads with distance, which makes it get quieter and quieter the further you move away, as we all know intuitively. The third is physical things that impede or dissipate sound between the source and receiver. And there's all kinds of things. Objects, buildings, noise walls, foliage, undulating topography, engineered noise control measures like barriers and enclosures, all those sorts of things. Those all fall into that category. And the last one is reflections, which are only occasionally relevant outdoors, but in rooms, it's very important. So inside, you can get reflections or multiple reflections of sound bouncing around and around. We call that reverberation. So we won't really talk about that too much, but reverberation and reflections can amplify sound and make it louder than it would otherwise be, because you're getting more sound ending up at a point than would normally otherwise get there. So each of those four things affect the loudness, and they also present sort of the strategies for how we might control noise. And the first one is a bit of a no-brainer. Louder things are going to be riskier and more of a potential to cause disturbance. So when we're designing a site or picking a site, we want to be wary and mindful of how loud are these sources. Are there quieter things available? Can we find a quiet way of achieving the same thing without making as much noise in the first place? Then we won't have to try to use engineered noise control measures to make it quieter. And the next one is distance. So we're going to have a slide on that. Sound falls off or gets quieter with distance for the same reason that light gets dimmer with distance and gravity gets less with distance and heat gets less with distance, because the energy we're talking about is spreading over a bigger area. Without obstructions, sound is going to spread in a spherical way. And or if we've got a reflective ground plane below, a hemispherical way. But at any rate, you can sort of see the same amount of energy is passing through an area that's getting bigger and bigger. So the energy per unit area is getting less and less. In other words, the sound's getting quieter. We call this the inverse square law. You probably remember that from physics class. And when it comes to light, it works one way. It actually works the same for sound, but because we're measuring sound in decibels, it handily works out to 6 dB of decrease per doubling of distance. And that's other things being equal. So if there's no obstructions in between or anything else going on, or wind or whatever, just distance alone as you move away. So if we had 50 dB at 100 feet, you go to 200 feet, it's going to be 44 dBA. And you go to 400 feet, it's going to be 38 dBA. You go to 800 feet, it's going to be 32 dBA, and so on. It's going to fall off at 6 dB per doubling of distance. So distance in between is a very important factor, but beyond a certain point, because it's going and doubling, you want to get another 6, you got to go another mile. So that works really well in terms of the initial buffering distance, but beyond that, we often need other noise control strategies. The next most common one that everybody's probably seen or heard about is a noise barrier. That could be an engineered noise barrier as a noise control measure, or it could just be natural barrier. It could be a building, it could be foliage, it could be undulating topography that breaks the straight line between the source and receiver. The interesting thing to note about a barrier as a noise obstructing mechanism is that it only works in the region where it creates a shadow. An obstruction doesn't prevent noise altogether. Even though noise generally travels kind of in straight lines, it's not a particle, it's a wave. And so it actually does bend around objects by something called diffraction, same thing that creates the way prism breaks up white light into colors. Diffraction causes sound to bend around the edge of an object. So the amount of shadow you get controls how much sound will get through into that shadow zone. If we were tall enough to see over the barrier, we get no attenuation whatsoever. As soon as the barrier breaks the line of sight, we get about 5 dBA of reduction, so about a 25% dB. And then the more this barrier obstructs the line of sight, the more attenuation we get, up to a practical maximum, theoretical maximum of about 20, practical maximum of about 5 to 10. The object has to be solid so that sound doesn't go through. And incidentally, trees are porous, so they don't really work well as a barrier. We're always asked about trees. Could we plant a row of trees? Well, a row of trees does almost nothing. To be effective, even marginally effective, to get about a 3 dB reduction from trees, you need about 30 yards of deep, dense bush, and it has to be tall enough to break the line of sight. I've just highlighted the 3 important things that happen when you have a noise wall. The main one is that you get this diffracted path over the top. As long as we build the wall heavy enough that not much sound gets through, and that usually means about 5 pounds per square foot, then the amount of sound that goes through it is going to be negligible. There's always going to be some that goes over the top and around the edges, and that's why we come up with this practical maximum of about 5 to 10 dB of a reduction from the barrier. And we do have to be careful, because you put up a barrier, you get a reflection off the bright side, and so somebody around on the other side might be louder for them. We have to be careful about that. Another common measure, particularly in that we see now in data centers, which are perforating across the continent, has to do with cooling fans. Because as with many industrial processes, there's a lot of waste heat from a data center. And so that waste heat is collected, I guess, with refrigeration or cooling systems, kind of like your home air conditioning. And that heat is usually dissipated using some kind of an axial fan, whether it's on a evaporative cooling tower or just a condenser unit. And so I'm showing here a standard axial fan. There are low noise fans. They're more expensive. Standard axial fan is just like a stamped tin blade, little rectangles, kind of like your home air conditioner maybe. Although you are seeing, even in home systems, an increasing number of these low noise fans. They've got aerodynamically generated forward curved blades. They've got an aerodynamic profile to them. Can't really see on this one, but it also has a sawtooth edge on the leading and trailing edge. It helps to reduce sound. And they can be about 5 to 10 dB quieter than a standard axial regular fan. And then there's ultra low noise fans that look like this. They're almost like a boat propeller. And they're really quiet. They can be 15 dB, sometimes 20 dB quieter. So a quarter as loud as the cheapo fan, but they are highly expensive. Even a 30-inch diameter version of this fan is usually on the order of $5,000 to $10,000. But they can be really, really quiet, and they're increasingly used as an option in cooling towers. They make these up to 30 feet big. Another interesting thing we can do with cooling systems that are a primary source of sound at data centers nowadays is to use variable speed drives on the fans, particularly at night. So if the cooling system is designed to provide adequate cooling during a hot summer afternoon, then even on a warm summer overnight, the cooling load is only going to be about half because the outdoor air temperature drops. And so we only need half the cooling capacity. Now, an interesting thing is if you get your half cooling capacity by shutting off half the fans, so we can reduce the airflow by 50%. If we do that by turning half the fans off, that gets you a 3 dB reduction, just by log math. And if you remember, that's only a barely or imperceptible change in sound level. So you don't get any bang for the buck if you just shut half the fans off. Yes, it's numerically a little bit quieter, but not really perceptually. But if we slow the fans down to half speed to get half airflow, we get a whopping 15 dB reduction, which is less than half as loud. It's about a 150% reduction in perceived loudness. So that's really quite effective to slow fans down. Well, what if it's not a fan, or what if we can't put a variable speed drive on? There are silencers that can be put on some types of fans. Those axial fans we were looking at don't lend themselves well to silencers because they can't push against very much back pressure. But there are silencers. They just have sort of parallel channels through them with absorptive material. They soak up a lot of sound. Those can be used on openings in buildings as well. There are acoustical louvers for ventilation air openings in buildings or enclosures. And for combustion sources like engines, of course, there's combustion silencers, or what's sometimes called mufflers. Not terribly different from what's in your car, just a lot bigger. For sources that emit sound from their housing or casing, like a power generation unit at a power plant, or at an industry, or at a data center, we might need a whole acoustical enclosure. Excuse me. And so this has walls that are designed to be sound insulating doors. What you can't really see here, but is also important, is that we need to get ventilation air in and out of this enclosure to cool the generator. This is an actual enclosure around about a 2 to 3 megawatt generator of the sort that are used a lot at data centers nowadays, or backup generators for industry. So they'll be sucking air in through a great big silencer, and the discharge here out the sides and out the end would also go through a silencer or an acoustically lined hood. You can actually see this unit on top is an emission control unit, but that also functions as an acoustic silencer and muffler as well. Less pipes at the top. And that covers the main. There are other esoteric ways of doing noise control, but those are the main ones: enclosures, silencers, barriers, picking quiet equipment, and making sure the site is far enough away from the point of reception that the sound levels are acceptable. Alrighty, that is the end of prepared material. I have a couple of optional slides if people ask certain questions. I'm happy to take any questions that you may have in whatever time we have left.
Yeah, for those that are still on, if you have a question, please feel free to ask it now while we've got Rob and his team on. Otherwise, we can also take your questions via email later and get those answered for you. I'm not seeing any, Rob, so that must mean that you answered everyone's questions before
Right,
they
I
had
covered
to
all the
ask
bases. Yeah,
them.
I'm going to see if I can figure out how to stop sharing. I don't know how to do that on Zoom.
Same way when you went to go share, you should just be able to click down on that button and stop sharing.
Now that I'm sharing, I don't see that screen anymore. See if I can find it down here.